Today we are going to cover mass-to-mass stoichiometric conversions. We've already covered mole to mole using the mole ratio, and we've covered mole to mass using the molar mass of the compound or element. The reason we're going to do mass to mass is when you work in a lab, the equipment we have is a triple beam balance or electronic balances to measure mass. We don't have a device to measure moles. So when chemists are working with a chemical reaction and want to produce a certain amount of product, they would need to be able to mass out how much reactant to start with. And at the end, they'll measure the mass of the product they form and compare it to what they should have formed. So we'll start by writing our molar highway. Again, the A and B just distinguish that we're working with two different substances. So I'm going to convert from the mass of A to moles of A, and I'll do that using the molar mass of A. We would need the periodic table for this. Once I'm at the moles of A, I can convert to moles of a different substance in the chemical reaction. We'll call that moles of B. And it's a conversion factor we've been working around with all week. It's the mole ratio. And you need the coefficients in the balanced chemical equation. And I just abbreviated balanced chemical equation BCE. And then finally, we're going to convert to the mass of B. And we're going to do that using the molar mass of B. Again, you'll need your periodic table. So we're going to do a conversion problem. We're going to convert from, or we want to find how many grams of tin 2 fluoride are produced by the reaction of 30 grams of hydrogen fluoride. I like to put a little flow chart underneath, which is what we'll do. It does say here excess tin, and I want to just clarify what this means. This means you have plenty of tin. You don't have to worry about running out of the tin with this reaction. It's kind of like when you're baking cookies and you're getting your ingredients together, at least in my house. We always have plenty of flour, excess sugar. What limits the ability to get the recipe done is how many Hershey Kisses, if I'm making Hershey Kiss cookies, how many chocolate chips, if I'm making chocolate chip cookies. Sometimes the number of eggs is my limiting ingredient, but usually I have excess flour and sugar. So in this chemical reaction, we have excess tin. We're limited in that we only have 30 grams of hydrogen fluoride. And we want to know how many grams of tin 2 fluoride we can produce. So I'm going to convert from grams of hydrogen fluoride to moles of hydrogen fluoride. Then I can come over and convert to moles of tin 2 fluoride. And then finally, 2 grams of tin 2 fluoride. Each arrow is a conversion factor. Kind of helps you picture where you're starting from and where you have to go. So I'm going to start with what I was given, 30 grams of hydrogen fluoride. The units I started with are going to move down to the bottom of my first conversion factor. And I can convert, you can see here that I'm at grams of hydrogen fluoride. I can convert to moles of hydrogen fluoride. That's a conversion I can make. The units moles of hydrogen fluoride at the top of my first conversion factor, I bring down to the denominator of my second conversion factor. Now I can convert from moles of hydrogen fluoride to moles of tin 2 fluoride. It's my mole to mole conversion. The only way to convert from one substance to another is use that mole ratio. We'll use it in every type of conversion we do. And so then the units at the top, the numerator of my second conversion factor, will go to the denominator of my third conversion factor. And I can convert from moles to grams of tin 2 fluoride, which is what I was asked for in the problem. Again, dimensional analysis, you set up the units first, and then you go in and put numbers in. So I'm going to go in and fill in my numbers based on my units. So this first conversion factor, I have moles and grams. That's molar mass of hydrogen fluoride, which is something I have to calculate. I list my elements. I list how many. I use the periodic table for the mass. And then I add them together. Remember, for sig figs, it's the least number of decimal points behind, least number of places behind the decimal point. So it's 20.01 grams. So 1 mole is 20.01 grams. For the next conversion factor, it's mole ratio. So I need to look at the balanced chemical equation, and I look at the coefficients. If there's not a coefficient, like there's no coefficient there, it's just a 1. And then here I have a 2. So for every 1 mole of tin 2 fluoride formed, I need 2 moles of hydrogen fluoride. Then the last conversion factor is the molar mass of tin 2 fluoride. And so I list my elements. I list how many. I use the molar mass from the periodic table. Multiply. And then add, and remember it's the least number of places behind the decimal point for sig figs. So 1 mole of tin 2 fluoride is 156.7 grams. So now I've set up all my units. I've set up all my numbers. I'm going to go and multiply the top, multiply the bottom, divide, round for sig figs. And so it looks like, remember, mole ratio does not count for sig figs. We don't use it to determine sig figs because it's a counting number. It looks like I have 4 sig figs for my molar masses and for the mass I started with. So I'll need 4 sig figs in my answer. Units cancel diagonally. It's very important for these problems you write the compound or element that is with your units, or else you will be confused. 4 sig figs, 117.5 grams of tin 2 fluoride. So that mass is theoretically what we should produce if the reaction runs to completion, if it if you don't have any errors or any spills. And so what chemists can do is calculate a percent yield. And so when you bake or cook, you may do this without even thinking about it. You look at the recipe and maybe it says it'll make 4 dozen cookies, but you only actually make 2 dozen cookies. So then your percent yield is 50%. It didn't really give you as many cookies as you expected. So percent yield, remember it's the part divided by the whole. So it's the actual yield, and I will define these terms, divided by the theoretical yield times 100. Or you can think actual divided by theoretical. And so the actual yield is the measured amount in lab. You carry out the reaction and you find the mass of your product. Theoretical yield is the calculated amount. All of these calculations that we've been doing are giving us our theoretical yield. And so chemists use percent yield to determine the efficiency of a reaction. And so my example with baking cookies, if my theoretical yield is 4 dozen and my actual is 2, I only have a 50% yield. That's not a very good percent yield. So let's do a problem. What is the percent yield if the measured amount of product in lab was 0.71 grams? So measured amount of product in lab was 0.71 grams. Measured amount means actual yield. And the calculated amount was 0.86 grams. So percent yield equals actual divided by theoretical times 100. Sig figs do count. You don't use the 100 to determine sig figs, but my masses each have 2 sig figs. So my answer should have 2 sig figs. It's 83%, which is not a bad percent yield. You have practice problems to complete over mass-to-mass calculations and percent yield problems. You will have a mass-to-mass conversion and a percent yield problem on your daily assessment the next time you're in class. And remember, you're working to earn those stoichiometry stars and the extra credit points if you earn all 4 stoichiometry stars. If you have any questions, please send me a message or attend our office hours.